Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. Lesson 15, what is a trigonometric identity? So this starts out with a classwork exercise. There is some behind the scenes, there's a behind the scene example, which I'm not going to do in the video. Exercise 1 through 3 says, recall the Pythagorean identity. Sine squared theta plus cosine squared theta equals 1, where theta is any real number. Find the sine of x, given that cosine of x is 3/5. For x being between 0 and negative pi over 2. So a lot of times it's a good idea to just try to picture what it's giving us. And if we are between 0 and negative pi over 2, we are in this region right here. We're between here and here. So our answer is going to be in the fourth quadrant because that's our domain restriction. Okay. So what I'm going to do is I'm going to draw a triangle. Cosine of x equals 3/5. Well, cosine is opposite over hypotenuse. I'm sorry, adjacent over hypotenuse. So if the hypotenuse is 5, this is a circle with a radius of 5. So if this is 5, I need to draw a triangle where this side's 3, and this is 4, and this is 5. Okay, that's one way to think about it. But to solve this algebraically, all we have to do is write the formula. We're given a formula. What is my pen doing? Sine squared theta plus cosine squared theta equals 1. It says to find the sine of x. We're trying to find this. We're given that the cosine of x is 3/5. So we're just going to substitute this in for theta. Our x is theta. So if the cosine of x is 3/5, then the cosine of theta is 3/5 squared. So that would simplify to the sine squared theta plus 3/5 squared equals 1. Okay, simplifying that, we get the sine squared theta plus 3 squared is 9, 5 squared is 25 equals 1. Subtract 9 over 25 from both sides, and we get the sine squared theta equals. So if this was 25 over 25 and we're subtracting 9 over 25, we're left with 16 over 25. And in order to finish this, we take the square root of both sides. So when I take the square root of both sides, I get the sine of x equals the square root of 16 is 4, and the square root of 25 is 5. Remember that when you take the square root of something, you get a positive or a negative solution. But now we have to focus on where we are in the unit circle, and we are in the fourth quadrant. And sine is negative. So sine is positive here, sine is positive up here, sine is negative, sine is negative. Sine is your y. So I only want the negative value, so I'm going to just eliminate the positive. So my answer is negative 4/5. Okay, part B says find the tangent of y given the cosine of y equals this. So again, we're going to write sine squared theta plus cosine squared theta equals 1. And then we're going to say sine squared y plus, and if cosine of y is negative 5/13, then cosine squared of y would be that negative 5 over 13. squared equals 1. So we get sine squared of y equals, so think of this as 13/13ths, and we're adding 5/13ths to it. So that would be 18/13ths. Okay, it would help if I squared it first, right? So let's do that. I forgot to square. So this is going to be plus, now a negative squared is going to become a positive. 5 squared is 25. 13 squared is 169. So that's going to equal 1. So then we get the sine squared of y is going to equal 169 over 169 minus 25 over 169. So 169 minus 25 is 144 over 169. So I'm going to take the square root of both sides. Okay, and I am going to get the sine of y equals 12 over 13, and it's plus or minus. Now I need to focus on this. We are between pi over 2, which is here, and pi, which is here. Okay, this is pi over 2 and pi. So we are in the second quadrant. Sine is positive there, so I don't want the negative. So I erase this. And the sine of y is 12/13. Cosine is negative 5/13. And it asks for the tangent of y. So remember that the tangent of something, tangent is sine over cosine. So the tangent of y is going to equal the sine of y, which is 12 over 13, divided by the cosine of y, which is negative 5 over 13, multiplied by its reciprocals. The 13s cancel, and we get the tangent of y equals, and we're going to have 12 over 5, but it's negative. And that is the tangent of y. All right, part C says to write tan of z in terms of cos z, for z being between pi and 3 pi over 2. All right, keep in mind that tangent equals the sine divided by the cosine. And I guess I should have a theta in all these. Okay, tangent is sine over cosine. If we're going to be in terms of cosine, I need to find a value for sine in terms of cosine. So I'm going to use that Pythagorean identity to do that. So if I say that sine squared z plus cosine squared z equals 1, I need to solve for sine to get it in terms of cosine. So I'm going to subtract cosine over the other side. So I'm going to say sine squared z equals 1 minus cosine squared z. Okay? And in order to get rid of that and get sine all by itself, I take the square root of both sides. So that is going to give me the sine of z equals the plus or minus square root 1 minus cosine squared z. Okay, now let's look at where we're talking. Where's pi? Pi is right here. Where's 3 pi over 2? Right here. So this is our restriction. This is where we're talking in the circle. And if I am looking for sine over there, sine is negative. So I don't want the positive, I only want the negative. So I have sine of z equals negative square root 1 minus cosine squared z. Now I'm going to use this and say the tangent of z is equal to the sine of z, which is this in terms of cosine. So it's going to be the negative square root 1 minus cosine squared z divided by cosine Z, which is just cosine Z. So there is the tangent of Z in terms of cosine. All right, page 2, number 2 says to use the Pythagorean identity to do the following. What's a Pythagorean identity? Sine squared theta plus cosine squared theta equals 1. Okay, so part A says to rewrite the expression cosine theta times sine squared theta minus cosine theta in terms of a single trigonometric function. Okay, so this is two terms, so divided by a minus sign. So if you focus on this as one term and this as one term, what do they have in common? They both have a cosine of theta. So I can factor out a cosine of theta. So that will give me the cosine of theta times sine squared theta minus 1. So if I distribute this, I'd get this minus cosine theta times 1. So there it is, cosine theta times sine squared theta minus 1. Well, that's where they're saying use the Pythagorean identity. So how do I get sine squared theta minus 1 out of this? By subtracting 1 over here, okay, and subtracting cosine squared theta over here. So if you can do that all in one step, you would get sine squared theta, subtract 1 over to the other side equals, subtract cosine squared theta over to this side. I guess this should be here. Okay. And so sine squared theta minus 1 equals, and I subtracted, so it's negative. Negative cosine squared theta. So I can replace this now. So cosine of theta times a negative cosine squared theta. Now when I multiply these, a positive times a negative is negative. Cosine times a cosine squared is cosine cubed theta. Okay, so there it is. And that would be for all real numbers, for all reals, for all real theta. Let me just write that. But the upside down A means for all real numbers, theta. Okay, part B. Rewrite this expression in terms of a single trig function. State the resulting identity. So we have 1 minus cosine squared theta. That's a part of the identity. So how do I get that out of this? Well, 1 minus cos squared. Cos squared's got to be over here. So that would be by subtracting cosine squared theta from both sides. So I would get sine squared theta equals 1 minus cosine squared theta. Oops. Whoops. I don't know what I was writing. Theta. And that should be there. Okay, so sine squared theta equals 1 minus cosine squared theta. 1 minus cosine squared theta is sine squared theta. Okay, and that's going to be times cosecant theta. Well, sine squared theta, think of that as over 1, times cosecant theta is 1 over the sine of theta. So combine these, I get sine squared theta divided by sine theta. So that's just simply the sine of theta for all real numbers, theta. Okay, my fault. I wasn't thinking of the prior line here. We have a restriction. Sine theta cannot be 0. When is sine theta 0? Where's my unit circle? Sine theta is 0 at 0 and pi. So sine theta for all, do I want to say for all? For all theta that are not equal to multiples of pi. Okay. Okay, part C, this one's a little challenging. It says find all solutions to this equation in the interval from 0 to 2 pi. So it's one full rotation of the circle, okay? Draw a unit circle that shows the solution. So there's my unit circle, and I will put the solution in there when we're done. So there's a sine squared theta here. There's a sine squared theta in the identity, so that's what we're going to work with. And this is plus a cosine theta. So let's get this all in terms of cosine. So we have 2 times the sine squared theta. So what can I do to get sine squared theta in terms of cosine? Subtract cosine squared theta over to the other side. And that will give me that the sine squared of theta is going to equal 1 minus the cosine squared of theta. So I'm going to substitute this in place of sine squared theta. So I'll do that right below here. We're going to have 2 of them though. And sine squared theta is 1 minus cosine squared theta. And that is going to equal 2 plus cosine of theta. Okay, so that's step 1. The next step is I'm going to distribute the 2. So 2 times 1 is 2, minus 2 times cosine squared theta is 2 cosine squared. And I should have these here. Theta equals 2 plus cosine theta. Do I need those? I don't know. Let's just put them. Okay. So the next step we're going to do is, let's think about this a second. 2 minus 2 cosine squared theta equals 2 plus cosine theta. Okay, I have a 2 on both sides. So subtract 2 from both sides, they go away. That will simplify to 2 cosine squared theta equals cosine theta. Okay. All right. So now if I get those all on one side, it's going to be negative 2 cosine squared theta minus cosine theta equals 0. Okay, multiply all this by negative 1 and we'll get 2 cosine squared theta plus cosine theta equals 0. All right, so now I have a binomial, if you will, with a cosine function in both terms. So I'll factor that out. So that's going to give me the cosine of theta times 2 cosine theta okay, I'm factoring out a cosine. So that's going to be 2 times cosine theta plus 1 equals 0. Okay, so we have a product equal to 0. That is the 0 product property. So either cosine of theta equals 0 or 2 times the cosine of theta plus 1 equals 0. So to solve this for cosine theta, I would subtract 1 and then divide by 2. So that would give me the cosine of theta equals subtract 1, divide by 2. Cosine of theta equals -1/2, or the cosine of theta equals 0. Okay, so where is cosine theta equal to 0? Over 0 would be here or here. But then we also want cosine of theta equal to -1/2. So here's one solution right here, and that is the point 0, 1. Here's one solution right here. That is the point 0, -1. That came from this. Or cosine of -1/2, which would bring us over to here and up onto the circle. So let me draw a line over to that. So we're going over here. Let me make that thinner. That looks all right. And then something like that. Okay, so this is the point -1/2, comma, and if you know your unit circle, this has got to be the square root of 3/2. Okay, and I'm also going to get -1/2, I can go up here, or -1/2, I could go straight down here. So I will do another line segment going to the negative side, which would be down here, giving us the solution, which is right here, of -1/2, comma, negative square root 3/2. Okay, so there are our 4 solutions. Find the solutions to this equation in the interval 0 to 2 pi. Well, the solutions are -1/2, comma, root 3/2. Okay, and so now we want to find what theta is in those locations. So now we want to know what theta is. Okay, so I just drew these in to help you out with how to find out what theta is. So if we cut one of the quarters of the circle, first quadrant, break it down and draw this line segment here, that's pi/4, because this is pi/2 and this is pi. And we can keep going, but I only went out to pi. So this is pi/4, pi/2, 3 pi/4, 4 pi/4, or pi. And then this is pi/6, 2 pi/6, 3 pi/6, which reduces to 2 pi/3. And there's our answer. Okay, 2 pi/3. This is 3 pi/3, or pi. Actually, this is 4 pi/6, 5 pi/6, 6 pi/6, 7 pi/6. This is 8 pi/6, which is 4 pi/3 when you reduce it. So our solutions are, so if cosine theta equals these values, then we can say that theta equals, and our answer is pi/2, comma, pi/3, comma, 4 pi/3, comma, and if this is pi/2, 2 pi/2, 3 pi/2, this is 3 pi/2. And those are the 4 solutions. Okay, I forgot my little 2 that was right here. This is not pi/3, it's 2 pi/3. I always review my solutions when I'm done, and you should do the same. Pi/3 was over here, 2 pi/3, 3 pi/3, 4 pi/3, and so on. Okay, so these are the 4 solutions. Okay, page 3 brings us to problem number 3, which asks which of the following statements are identities. If a statement is an identity, specify the values of x where the equation holds. So pause the video, see if you can do these. Unpause the video, come back and see how you did. Okay, so assuming you paused the video and done this, let's take a look. So A is the sine of x plus 2 pi equals the sine of x. So if you think about that, wherever x is on the unit circle, If you add 2 pi to it, you're going to go around the circle, one full rotation, and end up right back where you were. That is true for all values. So therefore, this is an identity defined for all real numbers. Part B, secant of x equals 1. Do you remember what secant x is? What is secant? Secant is the inverse of cosine. Secant is 1 over cosine. So cosine cannot be 0. So we would say this is not an identity. The functions are not equivalent for all real numbers. For example, although secant of 0 equals 1, secant of pi over 4 equals the square root of 2. The functions have equal values only when x is an integer multiple of 2 pi. Additionally, the ranges are different. The range of f of x equals secant x is all real numbers y such that y is less than or equal to -1 or y is greater than or equal to 1, whereas the range of g of x equals 1 is the single number 1. Okay. Okay, so let's talk about this a little bit more to explain what they're saying. Secant of 0, well, that'd be 1 over cosine of 0. 1 over cosine of 0. Cosine of 0 is right here. Cosine of 0 is 1. That'd be 1 over 1, which is 1. So that's true. But if I go to pi over 4, which is right here, remember that is the point root 2 over 2, comma, root 2 over 2. The cosine is this, root 2 over 2. Secant is 1 over the square root of 2 over 2, which equals 2 over the square root of 2. And you multiply by root 2 over root 2, you get 2 root 2 over 2, and that cancels, and that's where the square root of 2 came from. So the secant of pi over 4 is the square root of 2. They have equal values only when x is an integer multiple of 2 pi. Okay, and then they talk about the ranges. So these cannot be between -1 and 1. And the range of g of x is 1 and only 1. Okay, so what they're trying to say here is they're calling secant x f of x and g of x is 1. So they're basically just saying f of x equals g of x. And the range of 1 is less than -1 or equal to, or 1 or greater. And the other one is just simply 1. So their ranges are not the same. Part C says the sign of -x equals the sign of x where the functions on both sides are defined. Okay. This is not an identity. This statement is only true when sign of x equals 0, which happens only at integer multiples of pi. So it'd be at 0, pi, 2 pi, 3 pi, 4 pi, and so on. Not true anywhere else on the unit circle. Part D, 1 plus tan squared x equals secant squared x, where the function on both sides are defined. Okay, this one, let me try to explain this. If I have sine squared x plus cosine squared x equals 1, that is my Pythagorean identity. Secant is 1 divided by cosine. So if I divide this by cosine squared, or just cosine x, divide everything by cos x, watch what happens. Actually, cosine squared x. So sine squared x over cosine squared x is going to give me the tangent of x. Tangent squared of x. Cosine squared x divided by cosine squared x is 1. 1 over cosine squared x is secant squared x. So all it is the Pythagorean identity with every single term divided by cosine squared x. Okay, so let's put this into words now, but that was just an example of where it comes from. So it is an identity. The functions are on either side are defined for theta not equal to pi over 2 and multiples of pi in that. Okay, E says sine of pi over 2 minus x equals cosine x, where the functions on both sides are defined. So the way I'm going to explain this one is just simply to draw a right triangle. And remember that if we do have a right triangle, then theta is here and 90 degrees minus theta is here because the two acute angles in a right triangle are complementary. So if the sine of pi over 2, which is 90 degrees, minus x does equal the cosine of theta, or x. So this is an identity defined for all real numbers. And finally, part F. Sine squared x equals tan squared x for all real x. So if I was thinking of putting this all in terms of sine, this would be sine squared x equals sine squared x divided by cosine squared x. Think about that for a second. All right, so now let's answer the question. This is not an identity. Sine squared x equals tan squared x is only true where sine squared x equals sine squared x over cosine squared x. So cosine squared x equals 1, and then cosine x equals 1, or cosine x equals -1, which gives x equals pi times some multiple of k for all integers k. For all other values of x, the functions on the two sides are not equal. Moreover, tan squared x is defined only for theta not equal to pi over 2 times some constant times pi for all integers k, whereas sine squared x is defined for all reals. Okay, and there's another argument here for why the statement is not an identity. Sine squared of pi over 4 is root 2 over 2 squared, which equals a half. But tan squared of pi over 4 is 1 squared, which is 1, and 1 does not equal a half. So that is a counterexample, and this is a reasoning statement. Okay, page 4 brings us to the end of lesson 15. Review the Pythagorean identity on the lesson summary and go to your problem set.